So the very first thing I have here is kind of a follow-up on what we were talking about last class with the magnetosphere. Remember we talked about how the Earth's magnetic pole is weakening and moving, and I found this several-minute video. It has really good graphics that kind of goes through, talks about some of the concepts, talks about some experimental work that's happening right now. Let's see if I can make this work. Here we go.
Heard that Earth's magnetic poles tend to move around. I mean, so do the geographic poles, but magnetic north and south are really mobile. And magnetic north in particular is moving real fast, like way faster than we thought it would. And the scientific community is coming up with some really exciting and creative ways to figure out why. The prevailing theory about why our planet has a magnetic field in the first place is because of what's underneath us. Dynamo theory, as it's called, is the idea that the molten metals of the outer core, like iron, are being convected, basically swirled all around the Earth's interior, around that solid inner core. This continuously creates electric currents as charged particles move through this liquid metal, and in combination with the rotation of the Earth, it becomes what's called a dynamo, the source of the magnetic field. This also explains why the magnetic poles are not necessarily fixed points, because the liquid that creates that magnetic field is turbulent and always shifting, and the poles move as the fluid does. Right now, for instance, the North Magnetic Pole has been slipping down into Siberia for the past 150 years or so, and it's speeding up. Our magnetic field actually has a name. It's called the magnetosphere, and it plays a crucial role in making Earth a habitable planet. It wards off much of space's harmful radiation, like cosmic rays, acting like an essential protective cloak around the Earth, which is one reason why scientists and governments are so invested in knowing how it works and how it will behave, like the World Magnetic Model, for example. This huge and innovative computer model of Earth's magnetic field behavior is used by many international bodies as the guiding standard on what the world's magnetic field is up to. It combines sensor measurements of the field's strength and position, measurements which are then used in simulations of the geodynamo's past, present, and future behavior. The WMM releases updates to the model every 5 years, but in 2019 it was forced to release a mid-cycle update because magnetic north has been sauntering vaguely downwards much faster than anticipated. The perfect example of the fact that even though we're measuring and predicting to the best of our abilities, the geodynamo is too unpredictable and complex to make a truly complete model of it. That uncertainty means scientists are also looking for experimental ways to further probe the Earth's magnetic behavior, which typically involves creating models of the Earth out of liquid sodium, which is quite the commitment because sodium is a highly reactive metal that is extremely difficult to handle and likes to spontaneously burst into flame. New sodium ball experiments are being used in several labs worldwide, and in combination with improvements in computing and machine learning, could help us gain more insight into how Earth's magnetic field will change and how we can prepare for it when it does. Because what does a shifting magnetic field actually mean for us? Flipped poles would mean the names of Earth's hemispheres may be a bit confused for a while, and compasses would point in the opposite direction than they did previously. But more importantly, as the poles shift around, the magnetosphere could get weaker, with several smaller magnetic poles popping up in other places around Earth. A weakened magnetosphere means many things. The northern lights will be visible in new parts of the world, for a start, and all our satellites would need to be extra fortified against radiation, or we risk them getting totally fried by space weather like solar wind. Electronics here on Earth would be extremely vulnerable to interference and destruction by space radiation too, like our power grids. And that's not even mentioning the human health effects of being exposed to much higher degrees of radiation from space, which, let me tell you, are not great. We know from studying magnetic inclusions that Earth's magnetic field has flipped entirely in the past. They trade places about every 300,000 years or so, but it's been over double that amount of time since the last time we know they flipped. So we are long overdue for some magnetic migration, and it's happening fast. And scientists are working hard to understand why and how they move, and what exactly it may mean for us. And they do. The next update to the WMM is expected in early 2020. Do you want to know more about it when it comes out? Let us know down in the comments below. Make sure you subscribe to Seeker for all your science news, and for more on surprising things inside the planet, check out this video here. As always, thanks for watching, and we'll see you next time.
Okay, not a lot of new material there, but maybe some graphics that'll help reinforce some of the concepts we talked about. Okay, now we kind of move away from the general background, and we are going to spend the next month or so talking about water. And like I mentioned earlier, we'll start small. We'll start at the atomic level and go up from there. We'll talk about how water behaves. Water is a really unique substance. There's nothing else like it in the natural world. And some of the things we'll talk about today, I think, will sort of drive the point home. Now, this is a course on environmental geology. And we talk about the environment, we talk about how humans interact with the natural world. Now, when it comes to water, water behaves in such a unique way that we're going to spend a fair bit of time talking about its properties, what it does, how it responds to different stimuli out in the natural world. So what I want you to do is kind of a precursor to that is I want you to spend about 5 to 10 minutes. Let's just go 7 minutes. We'll start at 11:20 again. I want you to think about water, maybe look at water. Some of you brought water bottles with you. Look outside. Some of you have computers. You can get on the internet and get a nice ocean scene. I want you to find some water, inside, outside, or in your brain. You've all dealt with this substance your entire life. I want you to list as many properties, observations, things you know about water that you can. And the list will be pretty extensive. You know a lot about water. So like I said, going outside, thinking about it outside, thinking about time you spent on the beach, watching waves crash, or spent floating a river maybe in the last few weeks, or whatever, should give you some observations, insights about how water behaves in the real world. And don't forget, water's not only a liquid. When we say water, we tend to think, oh, you know, the nice runny stuff. Well, water behaves in ways other than a liquid. Think about that water, okay? So I'll give you 7, 8 minutes. Just list as many as you can, and then we'll kind of discuss them and bin them and categorize them and do all that stuff. Okay, I'm looking out at your papers, and I see most of you probably have, I'm seeing like 10 to 15 things, right? I bet if I let you sit here long enough and gave you some water to play with, I bet you could come up with 30, 40, 50 things in the course of a couple hours. And given long enough, you come up with a list that's pretty extensive. You guys know a lot about water. So what are some of the things on your list? It can be simple, it can be complex, I don't care. Yeah?
Water can be a liquid, gas, or solid.
Liquid, gas, or solid. Okay, it can exist in 3 states. Yes?
The chemical composition is H2O.
H2O, that's really important. That's something we're going to talk about here in a minute. Water is H2O, 2 hydrogens bonded to an oxygen. What else? Yeah?
Water on Earth is affected by gravity in space.
Yeah, water responds to gravity. It responds to external forces. Water flows downhill. Yeah?
It's self-adhesive.
Say again?
It's self-adhesive.
It adheres to some things, doesn't it? I don't know if you ever did this back in like grade school or whatever, but you can take a piece of toilet paper and stick it in water, and the water will actually climb up the toilet paper. That's actually kind of unusual. Not all substances will do that. If you did that with more of a petroleum product, it wouldn't do it hardly at all. There's a reason water does that. We'll talk about that in a minute. Yeah, it has adhesive, cohesive, and capillary properties. It makes it really interesting. What else?
It expands when it freezes.
Okay. Now we talked about water being a unique substance, right? There are 2 things that make water so different than all the other substances. That is one of them, is that when it freezes, it actually expands. Now, last class we talked about the effect of heat on atoms, right? What does heat do to atoms? Makes them vibrate more, right? So if you add heat to something, those things vibrate more and they tend to take up more space, right? When you take heat away, they vibrate slower and they tend to pack together more tightly and become more dense. And especially when they change phase from liquid to solid. As they become a solid, they join together in these really tight arrangements, okay? And just about every substance we know, when you freeze it, it shrinks. Water actually expands, and it expands by about 10%, which is a lot, which is how I spent half my damn day yesterday, because we're supposed to have these super cold temperatures. I've been watering my lawn and stuff like crazy to keep it from dying, but now we have water in all these exposed pipes in our sprinkler systems and outside, and when it gets cold, what happens? Any water that's in the pipe expands by 10% and lots of pipes break. And if you've owned a home or rented and had this happen, it's a pain in the ass when your pipes break. There's nothing worse than water just spewing everywhere. And it's happened to me in the past, and hopefully it won't happen to me tonight, but you never know. So this water expansion thing is a big deal. And because ice expands, where do you find it when it comes in contact with liquid water? It's on top, right? Yeah, water freezes and stays on top because it's less dense. And that's really different too. A lot of other substances, if it got denser, that ice would sink to the bottom and things would freeze from the bottom up. And think of how different aquatic life forms would be because of that. You know, now things are able to survive in lakes because they get trapped beneath this icy layer, which acts like rocks and kind of keeps things insulated. And because it expands, that's why we get a lot of the erosion that we get on mountain areas. That's one of the primary agents, is liquid water getting in the cracks and then freezing at night, expanding and breaking the rock apart. So the Earth is really different than its other neighbors in the solar system because we have so much water. Erosion rates are much higher here, and that's one of the big reasons, is water's ability to expand when it freezes. And we'll talk about why that happens. It has to do with how the molecules put together. So really interesting. You think H2O, simple molecule, right? This molecule isn't simple at all. Really complex. What else was on your list?
water rises from the ground and falls from the sky?
Okay, water falls from the sky, and it can actually evaporate back off the land as well. And in addition to just evaporating, it can also transpire, which basically means plants breathe it out. So, yeah, we have this thing called the water cycle. We have these great masses of water on Earth, the oceans. They evaporate. That water vapor goes in the atmosphere, condenses in clouds, rains back down on Earth, or snows back down on Earth. That water runs across the surface. Some of it soaks into the ground and replenishes our groundwater system. Some of it's sucked up by plants, and some of it runs off across the surface into streams and rivers, which ultimately try to head back to the ocean. So we have this whole cycle on how water moves around from different places on Earth. What else? Yeah.
It's necessary to pretty much all forms of life here.
Yeah, virtually every form of life that we know of requires water. Now, scientists have always been thinking about potential life forms on other planets, and could we have life without water? And that's a big topic of debate right now. Right now, we don't know really of many forms of life that can survive very long without any water at all. So it's absolutely necessary. We know it's necessary for us, but it's necessary just for most life forms that we know of at this point in time. What else?
Too much water can kill you.
Yeah, not enough water can kill you. Too much water can kill you. Yeah, if you don't get enough water, what's that called? Dehydration, right? You go outside, you don't drink water for a couple days, you're not going to live, right? You can go much longer without food than you go without water. You can also kill yourself by drinking too much water. It's a condition called hyponatremia. It's when you drink so much water that it basically dilutes your systems and your salts are out of balance. Ultra distance athletes had a lot of trouble with this back in the 80s and 90s when people started doing these ultra distance runs and these Ironman events and cycling across the country. They would just drink water, and a lot of them would get really, really sick. And they're sweating out all these salts. They're not replacing the salts. They're just replacing water. And your heart, all your internal organs requires the right salt balance. So that's when Gatorade and all those things started coming out, sports drinks, because it replaces the salt as well as the water. So too little water, dehydration. Too much water, hyponatremia. We have to keep our water intake in a certain range or we get sick and eventually die. So we're completely dependent upon it. What else?
It's conductive.
It's conductive? Yeah. In terms of conducting what?
Like electricity.
It can conduct electricity. Yeah. It can conduct heat. Things can move through it. The other thing is, what's unique about the ocean compared to, say, a lake around here in Colorado? What's the biggest difference between ocean water and that lake water? Water can dissolve things really well, but not everything dissolves the same way in water, right? If you put salt in, salts dissolve really well in water. Alcohol dissolves really well in water. What's something that doesn't dissolve really well in water? Oils. Oils don't dissolve well in water at all. And there's a reason for that. It has to go back to this little molecule we're going to talk about in a few minutes. So water is a solvent. We have solvent is something that dissolves other things. The other things are then called solute. So solute dissolves in a solvent. Water is kind of a universal solvent. It dissolves lots of stuff. It does dissolve oils to the tiniest of degree, but for the most part, those two will separate. Oils tend to be less dense than water, so they float on top. What else? Think of anything else that's on your list. Silly, not silly. That's a pretty good list so far, okay? All right, so with that as a starting point, all right, we listed your properties. All right, we're going to start with some basic chemistry. just to make sure everybody's on the same page. This will definitely be a repeat for most of you, but I'll try to get to a point later today where hopefully we have some new stuff coming your way. Now, I know some of you haven't had chemistry in a long time, so we are going to start at bare bones, early, easy chemistry. All right, we're going to talk about atoms. So we're going to review some terms. And actually, I think most of you would benefit from reviewing some terms. Okay, atoms consist of three different subatomic particles, particles that are smaller than the atom itself. So atoms are put together basically with three components. We have protons. These are positively charged subatomic particles that are found in the nucleus. Okay, positive charge in the nucleus. We also have neutrons. Neutrons, neutral, no charge. A subatomic particle also found in the nucleus, the center of the atom. And then surrounding this nucleus that has protons and neutrons are the third subatomic particle, the super tiny electron, which are negatively charged. And they can be found in distinct little orbits that surround the nucleus. You've all seen this. Okay. Out in nature, a lot of our substances are put together by bonds, chemical bonds, that arise because different atoms have different charges. We know that positive charges will be attracted to negative charges, and we know that like charges will repel one another. So charges are extremely important in governing how atoms work out in the real world. So geologists, we spend a lot of time thinking about charges of atoms. Now, atoms like to be neutral. You know, if they have a charge, they're going to attract the opposite charge. So they always tend towards neutrality. But out in nature, nature is a dynamic world. Things are bumping into each other, colliding, and at any given point in time, you have lots of charged atoms out in the world, okay? And we have some possibilities. One is that we could have a neutral atom. And in order to have a neutral atom, the charges have to balance out. So we have to have the same number of protons in the nucleus as we do the number of electrons that are out in the outer shell. So we have the same number of positively charged protons in the nucleus to balance out the same number of negatively charged electrons in the outer orbits. So if those two things are equal, we have a neutral atom. And that neutral atom will have no tendency to attract other charges. But like I said, out in nature, nature is a dynamic world, and we end up with atoms that are charged. Atoms that have a charge are called ions. Okay, first term that you've heard and maybe you've forgotten, ion is a charged atom, and there's two possibilities. One is that we could have more protons in the nucleus than we have electrons in the outer orbit. That means we have more positive charges than negative charges. That means that overall, the atom's going to have a positive charge. Positively charged ions are called cations. So cations, positively charged atoms, simply means you have more positively charged protons in the nucleus than negatively charged electrons in the outer orbits. Well, if you can have a cation, you can have the opposite case. The negatively charged ion is called the anion. where you have more negatively charged electrons in the outer orbit than positively charged protons in the nucleus. The neutrons, because they don't have a charge, don't enter into this. Doesn't matter how many neutrons you have, it's not going to affect the charge. Now we have cations, positively charged, anions, negatively charged. I don't care how you remember it. There's cat people and dog people, right? So just pretend you're a cat person. Cats are positive. If you have a friend whose name is Anne and you hate her, you could use that too. Okay? So cation, anion, charged atoms, can also have neutral atoms. All has to do with the balance between the protons and the electrons. Again, stuff you've all seen. Any questions? Okay, a couple more terms that you learned, maybe you forgot. Element. Definition of element is super simple. It's all atoms that have the same number of protons. It doesn't matter how many electrons it has. It doesn't matter how many neutrons it has. That doesn't even factor into it. Only thing that matters, number of protons. For example, the most common element in the universe is hydrogen. It's also the simplest atom out there. It simply has one proton. Doesn't matter how many neutrons it has. And in fact, hydrogen can have no neutrons. It can have one neutron. It can have two neutrons. Doesn't matter. All hydrogen atoms have one proton, and only one proton. Doesn't matter how many electrons it has. Doesn't matter if it's neutral, positive, negative, doesn't matter. It has one proton only. It's hydrogen. So up here we have the periodic table, and with every element up there, every element has a number. You see hydrogen is a 1. Go to the other side, helium is a 2. Lithium is a 3. Those numbers refer to the number of protons. Okay? So oxygen, right there. You see the number 8? Has 8 protons. Anything that has 8 protons is oxygen. Doesn't matter how many neutrons. Doesn't matter if it's an anion or a cation. All that matters, how many protons. 2 protons, helium. 8 protons, oxygen. We've identified over 90 naturally occurring different elements. So there's some atoms out there that have more than 90 protons. And then we've created some things in the lab that have over 100 protons. And most of them have a similar number of neutrons as well. So some atoms are big honking things with lots of stuff in their nucleus. And then you have something like hydrogen, and it's a proton. So these different elements vary in weight. If you have more protons and more neutrons, it's going to be a lot heavier element than hydrogen. I know you've all heard the term isotope. An isotope, you can define it a lot of different ways. Probably the easiest way to think about it is it's just a variation of an element. So you have oxygen. How many protons does oxygen have? 8. Always has 8. If it has more than 8 or less than 8, it's not oxygen. Always just 8. But oxygen can vary with the number of neutrons it has. Some varieties of oxygen have 8 protons and 8 neutrons. There's another variety that has 8 protons and 9 neutrons. And there's another variety that has 8 protons and 10 neutrons. So isotopes are elements that vary with the number of neutrons that they have. For example, we have something called O16. It's the most common variety of oxygen. It's oxygen, therefore it has 8 protons. This particular variety also has 8 neutrons. The O16, the 16, represents the total number of particles in the nucleus. So you have 8 protons plus 8 neutrons. That means 16 particles in your nucleus, O16. But we have a variety or an isotope of oxygen called O18. It's somewhat common, not quite as common as O16, but it's oxygen, so it has to have 8 protons. But in this case, it's O18, so it's 18 particles in its nucleus. If 8 are protons, that means that 10 of them have to be neutrons. They're both oxygen. But they're a little different, right? O18 is actually a little heavier. Actually a little more than a little heavier. It's about 12.5% heavier. And that's kind of significant. That means that out in nature, O18 will behave a little differently than O16. Just because it's a little heavier, that'll change its melting point. That changes its boiling point. It changes how easily it evaporates. So it behaves differently because it's a little heavier because of those 2 extra protons. Hydrogen is really interesting. Since we're talking about water, I put up oxygen and hydrogen because those 2 elements make up water, but there's also several isotopes of each, which means we have lots of different possibilities for making water out of these isotopes. The most common isotope of water is just H1. It's just a proton. But we have something called H2. It has a proton along with that. It has a neutron along with that 1 proton. Sometimes it's referred to as deuterium. Du2, H2, deuterium, but it's just a isotope or form of hydrogen. And we even have an H3 called tritium. It's a variety of hydrogen, but it's radioactive. You've all heard the term radioactive. What does it mean to be radioactive? It means that it's unstable. Over time, it's going to turn into something else. Okay? And H3 is actually highly radioactive. It has what we call a short half-life. You've heard the term half-life? Half-life refers to the speed at which a radioactive substance will break down into something else. If something has a short half-life, that means that it breaks down very quickly. Half-life is the amount of time it takes for half of your radioactive substance to break down into something else. So if you had a pound of tritium, H3, how long does it take for it to break down into something else? Well, different radioactive elements have different half-lives. Things like uranium, thorium, they have these ridiculously long half-lives, billions of years. H3 has a half-life of about 5.5 years. Breaks down super fast. There's not a lot of it out in nature. But we did something as humans back in the 1950s that put a ridiculous amount of tritium into the atmosphere. Any idea what we did in the 50s that would do that? Nuclear bombs, yeah. You know, back in the World War II, we dropped nuclear bombs in Japan. And then in the 1950s, we got into the Cold War with Russia, and we started building lots of nuclear weapons. And these were hydrogen bombs. And we were testing them down in the Nevada and New Mexican desert above ground. And when you detonate a hydrogen bomb, it produces a ridiculous amount of tritium, one of the forms of hydrogen. So we sent off lots of tritium into the atmosphere, and it bonded with other hydrogens and water to make H2O. And because half-life of 5.5 years, even today we still have some tritium in our atmosphere from those bomb tests back in the 1950s. But we've gone through 10 half-lives now, so the amount is dwindling. Anything older than that essentially has no tritium in it. So they use this as a forensic tracer, because if water is younger than 1950, it has some tritium in it. If it's older than 1950, it has essentially no tritium in it. It's old enough to have all of it broken down. There wasn't much to start with, and whatever is there has now been cut down so many times that it's essentially gone. So if you have water that has tritium in it, that water formed post 1950s. So how can you use that? Well, one of the ways they've used it is actually in Europe. They have old wines that are 100 years old, or old bottles of gin, or old bottles of scotch. And some of them are counterfeits, because a good old bottle of some of this alcohol can be... I was in Costco the other day, and they were selling a bottle of scotch for $15,000. Yeah, so I mean, there is a market for this really high-end alcohol stuff. And of course, whenever there's a market, you get counterfeits. And this is how they figure out whether it's a counterfeit or not. They just do a tritium test. If there's tritium in it, that means it's older than then it's younger than 1950. If there's no tritium in it, it's older than 1950. They can do that to find out how old groundwaters are, things like that. So you can use something like radioactive elements to solve some forensics problems. Isotopes, just a variety of an element. Any questions on that? Okay, somebody mentioned before that water can exist in several states: solid, liquids, or gases. We'll just go through a little background, then we'll talk about how water behaves and then how it's different in terms of its behavior with respect to solids, liquids, and gases than other substances. All right, in a vapor, you have atoms that have been heated to the point where they've broken all their bonds with their neighbors. And because they have so much heat, they're flying around the room sort of unencumbered by being bonded to anything. They're loosely packed. They're in rapid motion. They move in one direction until they hit something. Wall, tree, face, other air molecules. And then they ricochet and they go the other way until they run into something. So you're breathing in through your mask right now, and that's air. Most of that is nitrogen. About 1/5 of it is oxygen, and less than 1% of it is a bunch of minor gases. But they're all just bouncing around. There's lots of space between them. We're able to see through it quite easily. Liquids tend to be a little lower temperature, or maybe a little higher pressure. But the difference is that now they're physically touching one another. They're not bonded to the point where they are in a solid where they can't move relative to their neighbors, but they can feel the positive and negative attractions with nearby molecules, and they sort of stick to it a little bit. But they don't stick so strongly that they can't move. So water will exist in a confined space, but it can move. It can take the shape of the container it's in. And then we have solids. Atoms in a solid still move. They vibrate. Remember, if there's any heat available, an atom's going to vibrate. The only way to stop an atom from vibrating is to remove all the heat. That's a point physicists called absolute zero. I don't think we've even recreated it in a lab yet. And at that point, all atomic movement's supposed to cease. But it's only going to exist in theory or in some specialized lab down the way. It doesn't really exist in nature that we know of. Usually there's some heat, so that means that the atoms are going to move. But they move in fixed positions relative to their neighbors. Okay, I use this analogy in all my classes. So you guys are all sitting out there, right? Are you kind of moving? Yeah, you're wiggling, you're writing, you're typing, you're breathing, trying to keep your eyes open, whatever the case may be. So you're moving, right? There's heat in here, you're moving. But you're not moving relative to your neighbor. You guys haven't switched positions in the last 50 minutes, have you? So you're the atomic equivalent of a solid, right? You're moving, but you're in fixed positions. You know, in 20 minutes or so, I'm going to say, you know, see you guys next week or whatever. You're going to get up, right? And you're going to start moving, but you're in this confined space. You know, you might move to the back, you might move over here, you might come here. You're moving around, but you're here, you're still pretty close together. That would be the equivalent of a liquid. And then 2 minutes later, you're headed to the library, you're going to the parking lot, you're going to the bar. You know, you're just heading off as far as you can go, right? At that point, you have large separation between you, you're moving faster, you're the gas. So think of it that way, or I drew these really wonderful diagrams here. I think the one important thing is the solid. Solid's moving, right? Dust wiggling. But none of those molecules change positions relative to their neighbors. Okay? All right. I'll give you a second to write this out, and then we'll sort of go through this. What happened here? I'll let you write this down, then we'll sort of talk through it. Okay, on the previous page, we went through the states of matter, solid, liquids, gases, right? And different substances will be in a different state of matter depending on what its conditions surrounding it are. Okay, If you took water right now in this room, what would its state of matter be? There's some of it in the atmosphere, right? But what's the temperature in here? 70-ish, right? We're at Earth's surface. What state does water normally exist at 70 degrees at the Earth's surface? Normally a liquid. Some of it can evaporate. We're going to talk about evaporation and boiling. They're actually two different things. We'll get to that probably next class. But, okay, so mostly it's a liquid, right? If we go outside and it's 26 degrees, what's going to happen to that liquid water? Freeze, right? Or if we put that liquid water in a pan and heat it up above 200 and, I guess at this elevation, 208 degrees, it's going to do what? It's going to boil, right? So we know that heat, temperature is a measure of heat, will affect which of these phases we have. Now there's another variable that affects it as well, and that's pressure. You guys probably don't think about it so much because you're always under about the same amount of pressure, right? You're under pressure from the Earth's gravity pulling the atmosphere down on you. And as you go up into the mountains, you'll feel your ears pop, right? A little less pressure. But it doesn't vary that much. But as you go, let's say, deep into the Earth, you get lots of pressure. Or if you go to a small planet like Mars, or a small body like the Moon, not much gravity, not much atmosphere, very little pressure. So pressure can vary as well, and that changes the state of matter. The more pressure you have, the tighter together atoms are going to pack. You're squishing them. When you release the pressure, they have freedom to move about. Now, depending on the combination of pressure and temperature, you're going to end up with one of the three states of matter: solids, liquids, and gases. Okay? So let's think about this for a minute. Let's say you have high temperature. Okay? What is that doing to your atoms? Making them vibrate, right? They want to move. Let's also surround them with low pressure. So they want to move, and they can move, right? Nothing's confining them. What state of matter are you most likely going to have at really high pressure and really high temperature, really low pressure? You're going to have a gas, right? So over here we have what's called a phase diagram. And this one's for water. You can have phase diagram for alcohol. You can have phase diagrams for pretty much every substance out there. This one's for water. All the phase diagrams are a little different. So over on the y-axis we have pressure. Low pressure at the bottom. As we move up this chart, we get higher pressure. Along the x-axis, we have temperature. If we're to the left, low temperature, cold. As we move to the right of the diagram, more heat, higher temperature, higher movement. So we said gases are favored at high temperature, right half of the diagram, low pressure, bottom of the diagram. This region right here, right? Lower right part. That's where we should have a gas. What conditions would be most favorable for a solid, where the atoms can't move relative to their neighbor? Low temperature, they don't want to move. What about pressure? Squish them, right? Don't let them move. It's like a clown car, right? Put 20 people in a Volkswagen. They want to move. They're going to be wiggling around like crazy, but they're not going to be able to move because they're squished too much. So if you want solids, you want high pressure, squishing it, higher on your diagram, low temperature to the left side of your diagram. So upper right, you should have solids. Liquid is kind of the middle state, right? Okay. Let's talk about how water behaves. Water's phase diagram is different than every other substance. We'll get to that in a minute. But let's start at A, right here. Kind of a moderate amount of pressure, right? What about temperature? Pretty low, right? So it's getting squished some, and there's not much heat. So what should it be? Solid. And it is. So solid water is what? This is a piece of ice. Okay? in this first example, what I'm going to do, we're going to keep the pressure constant. Kind of like here on the Earth's surface. You're under some pressure, but it's fairly constant, right? So this is an example you know. You've seen this. This is what you're used to water behaving like. So let's start here. We have some cold water under the Earth's pressure, right? Let's heat it up. We're not going to change the pressure, we're just going to heat it up. So it's always going to stay right at this level pressure-wise, right? But as we add heat, it's going to increase the temperature and we're going to move to the right. So let's say we start at a piece of ice and we add a little heat and we go just a little bit to right here. What do I have? I still have ice, right? It's just a little warmer. Maybe it went from -10 to -5. Okay? I keep adding heat until I hit this line right here. This line separates the solid field from the liquid field. At that point, what's going to happen? It's going to change from a solid to liquid, and you know that is melting, right? So this is called the melting curve. Okay? Once I melt it, I have liquid, right? What if I keep adding heat? But I keep the pressure the same. I keep moving, right? Water's getting hotter. It's getting hotter. Getting really hot. Burns the hand. What happens here? Changes from liquid to gas. That process is called boiling, right? That's where all of the water molecules now have enough energy to turn from a liquid to a gas, right? So that's called boiling. Now if I just keep heating it up, what do I have? Hotter and hotter gas, steam, right? And I eventually end up at B. You could do this at home this afternoon. You could get a pan, aluminum pan, turn on the heat, plunk an ice cube in it. Enough heat's going to go in, you're going to watch it melt, and the water's going to get hotter and hotter, and it's going to bubble, and then it's going to go up into the air in your room, right? So that's changing phase just by increasing the temperature by adding heat. Pretty straightforward. You guys have all seen this, right? All right. Not sure why that all did that different. Okay. Now we're going to do something a little different. We're going to go the other way. Okay? We're going to start at B. What is B? It's gas. It's steam, right? Really hot water. Hot, so hot it boiled off, right? Now we're going to take the heat away. That's going to cool it off, right? Keep the pressure the same. So we're basically going to do a return path as to what we just did. So if I take heat away, how do I move? I move this way, it gets colder, colder, colder. What happens at this point? Yeah, what's that process called when you take a gas and turn it into a liquid? You said precipitate. There's another word. Condensation. So when we were going this way, that was called the boiling line, right? Going the other way, it's also called the condensation line. So it's boiling or condensation depending on which way you're going. At that point, you now have hot liquid water, right? Take away the heat, what does it do? Moves to the left until we hit this line, right? What happens at that point? It changes to a solid, which is called freezing. When we went the other way, it was called melting. So that's the melting freezing point. And then if we take heat away, what happens? It just gets colder, right? We get colder and colder water until we have A, which is ice, somewhere there. Again, something you've seen. This is what's happening today. All right? Yesterday we were here, outside. Today we're like right in there, right on the border. Okay, that's one possibility. That's one you're used to, but it's geology class, right? We talk about what goes on inside the Earth on other planets where the pressures are different. So let's vary the pressure on this and try something else. Okay. Now we're going to keep the temperature constant. Okay? Amount of heat is not going to change. So the atoms are going to vibrate the same throughout this process. But instead, we're going to increase the pressure. So let's start at A. What do we have? We have our piece of ice, right? And we're going to squish it. Okay, so how are we going to move on the graph if we squish it? We'll move straight up, right? Temperature is going to be the same, but we're going to increase the pressure. So if I increase the pressure, I start moving up, right? Da, 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 da. What happens here? It starts to melt, okay? I said before that one of the interesting things about water, there were two things that really made it unique, right? One was that when it freezes, it becomes less dense. This is the second one. No other substance that I know of does this. When you increase the pressure enough, it actually melts. That shouldn't happen, right? When you squish something, doesn't that make it harder for the atoms to move around? But with water, suddenly they start moving around. We'll talk about why next class. It has to do with the shape of the molecule. Water's the only substance I know that does this. And it allows water to behave in a way that's different from all other substances. If I strapped on some ice skates right now, and I took a running start across this room and tried to glide, what's going to happen? I'm going to face plant in a big way, right? But what if this floor was made of ice? I'm going to glide, right? What's going on beneath my ice skate blade? There's a lot of pressure, right? If you don't believe me, I'm going to put on ice skates next class, and I'm going to let you come up here and put your hand on the ground, and I'm going to step on your hand with my ice skate. All my weight is going to be on that little narrow blade, right? That means there's a tremendous amount of pressure under my blade. What's happening to the ice under my blade? It's melting. There's actually a little layer of water forming between my blade and the ice. A little friction too. So you're getting a little melting that's allowing me to glide. Other substances don't behave this way. When you pressurize them, they don't melt. So I have the friction of my blade against the friction of the floor, and it doesn't want to go anywhere. So it sort of self-lubricates. This is what allows glaciers to move. Glaciers can move under their own tremendous weight because you get little bits of melting, and that allows the ice to shift a little bit and behave more plastically. So kind of a unique thing. Only water does that. Here is a phase diagram that mimics just about every other thing in the universe. What do you notice about this phase diagram that's different than the water?
More pressure keeps it a solid.
Yeah, you see this melting freezing line? In water, it went back to the left, right? This goes up and to the right. Can you go anywhere in the solid field, increase the pressure, and become a liquid? No, this is how everything behaves out in the universe, except water. That makes water really different. And here on Earth, we got a lot of this stuff. Most planets in our solar system didn't get much of this stuff. So our entire planet behaves differently, primarily for those two reasons we talked about earlier. It's less dense when it freezes, and you can melt it by putting it under pressure. All right, let me do this really quick. So yeah, so you go from A, and if you increase the pressure, you just go up to B. Okay, let's go one more scenario here. A. All right, what do we have? Okay, now again, I am going to keep the pressure constant, and I'm going to increase the temperature. Okay, I'm going to keep the pressure here, increase the temperature. So I'm moving this way, right? What happens here? It goes right into a gas. It doesn't become a liquid. Okay? Anybody know what that process is called?
It's either deposition or sublimation.
Yeah, that part is called sublimation, okay, where it goes directly from a solid to a gas. Do you guys know any substance that does that naturally on the Earth's surface? You guys heard of dry ice? Yeah, that's solid CO2. It behaves this way. When it gets hot enough, it goes right to a gas, right? Never turns to a liquid. That's why it's dry. So you can keep your stuff cold without ever having to worry about it getting damp. Water will do that, but not on Earth. Here's where Earth's pressure is, right? You have to be somewhere where the pressure is much lower for water to do that. That's called deposition. If you go the other way, or sublimation, if you go the other way, remove the heat, you will form a solid, and that's called deposition. Okay, well, here we go. This is where Earth's pressure is, right? This is where planet Mars is. So if you go to Mars and go to this Mars on the surface, okay? Should you get liquid water on Mars' surface? No, it should be ice, and if you heat it up enough, it's going to go right to a gas, right? Where can I find liquid water on Mars? What do I have to do? What's that?
I was going to say underground.
Why?
Pressure, but
As you go deeper into a planet, what happens to the pressure? Goes up, right? And at some point on Mars, beneath the surface, there's going to be enough pressure to cause liquid water. So Mars on the surface might not be very habitable for us as life forms. It gets lots of radiation because it doesn't have a magnetosphere. It has no liquid water, has wild temperature swings. But if you wanted to find water, and therefore wanted to find life, where could you go? You'd have to go in the ground. And that's actually where most scientists think is the best place, the most likely place that we would find life on Mars. And in fact, if you go down a couple hundred feet, you will get enough pressure to form liquid water. It's possible that Mars has lots of life, but it's in the ground and it's evolved in the ground. I don't know if it's worms or just bacteria or what it is, but if there is life on Mars, the most likely place to find it is going to be where the pressure is high enough to enable a liquid phase. So I think I am just going to stick with that for today. Let's see. Okay, one announcement. No class on Thursday. Okay, I have a video I want you to watch. I will send you an email a little later today with the link. I'll have a couple of questions I want you to answer. They will count as a couple of points towards your first test. Super easy to watch. Do not dig the answers off the internet, especially Wikipedia. They're wrong. Okay? If you do that, I will know you did that because you will give me the wrong answer and you will get no points. Watch the video. It's about an hour. It's really good. It's about water use in Los Angeles. It talks about how a city of now tens of millions got enough water to survive when they only have a small stream that naturally flows through there. It's rather stunning how many people have been hurt, damaged, and killed over the last century just to provide Los Angeles with enough water to survive. The second worst dam collapse in United States history in terms of deaths you will see during this, and it's all to bring water to LA. So it's kind of interesting. I think it sets up what we're going to talk about a lot the rest of the semester. So I will send you the lab later today or tomorrow, along with the video for the lab later today, tomorrow. You get a couple weeks to finish it. Thursday, no class. Watch the video, And I'll see you back here a week from now. Don't forget your map. Don't forget to check your box off, okay? All right, see you guys later.